Our home galaxy floats in a void of staggering emptiness. This is the KBC Void, a bubble of near nothingness spanning billions of light years, and we are at its heart. By the end of this exploration, you will understand how this cosmic desert reshapes our entire story of the universe, from its birth to its ultimate fate. We will uncover why this vast emptiness might solve cosmology's greatest crisis and question whether our quiet neighborhood was essential for life to emerge. What does it feel like to live in the center of a cosmic nothing? To grasp the scale of our isolation, we first need to understand what a cosmic void truly is. For a long time, we pictured the universe as a fairly uniform place, with galaxies scattered evenly like flour in a mixing bowl, but that picture is completely wrong. The true structure of the cosmos is far more intricate and dramatic. Think of the universe not as a smooth soup, but as a vast three-dimensional sponge or a glittering cosmic web. In this web, the bright threads are filaments, long chains of thousands of galaxies pulled together by gravity. Where these filaments intersect, you find dense, glowing knots, the massive clusters and superclusters of galaxies. And between all these brilliant structures, there are the gaps, the empty spaces. These are the cosmic voids. These voids are not just small pockets of nothing. They are the dominant feature of the universe by volume, immense bubbles of near emptiness that can stretch for hundreds of millions of light years. Inside one, you might find only a handful of lonely, isolated galaxies drifting in the dark. To put that scale into perspective, if our entire Milky Way galaxy were the size of a dinner plate, a typical void would be an empty sphere roughly the size of the continent of Asia. That is the sheer, staggering emptiness we are talking about. Now, contrast that with the opposite extreme, a supercluster. Imagine a region of space so densely packed with galaxies that from within it, the night sky would blaze with the light of countless neighboring island universes. The difference in cosmic population is astronomical. A supercluster is a thriving, glittering metropolis. A void is a silent, sprawling desert. And as we've discovered, our home, the Milky Way, along with our local group of galaxies, is not in the metropolis. We are deep in the heart of the desert. This realization changes everything about our place in the cosmos. This cosmic desert has a name. Astronomers call it the KBC Void, named for the three researchers, Ryan Keenan, Amy Barger, and Lennox Cowie, who pieced together its staggering dimensions. Its scale defies easy comprehension. Picture a sphere of near nothingness roughly 2 billion light years across. To cross it, a beam of light, the fastest thing in existence, would have to travel for 2 billion years. Within that unimaginable volume, the bright threads of the cosmic web are almost entirely absent. It is a yawning chasm in the structure of the universe. And here is the fact that tilts your perspective. We are not on the edge of this void looking in. We are not even drifting somewhere within its expanse. Our Milky Way galaxy, along with our entire local group of galactic neighbors, sits almost perfectly at the dead center of this billion light-year bubble. We are the speck of dust floating in the exact middle of an empty cathedral, so vast its walls are beyond sight. This central positioning is not a coincidence of observation. It is a fundamental feature of our cosmic address. It means that in every direction we look, out to distances that encompass millions of galaxies, we are surrounded by an unusual and profound emptiness. Our quiet neighborhood is not just a suburb, it is the central plaza of the grandest emptiness we know. The evidence for our lonely address comes not from a single telescope image, but from a painstaking, three-dimensional census of the cosmos. For decades, teams of astronomers have been engaged in the ultimate mapping project, using instruments like the Sloan Digital Sky Survey to chart the positions of millions of galaxies. They do not just take pretty pictures, they gather data to pinpoint exactly how far away each galaxy is. The key to this cosmic cartography is a phenomenon called redshift. As the universe expands, it stretches the light traveling from distant galaxies, shifting it toward the red end of the spectrum. Think of it like the Doppler effect for a siren, but for light itself. The faster a galaxy is moving away from us, the more its light is stretched and the redder it appears. Because the universe's expansion is remarkably uniform, this redshift becomes a direct measure of distance. The redder the light, the farther away the galaxy. By measuring the redshift of millions of galaxies, astronomers can plot their locations in 3 dimensions, creating a map of the universe's large-scale structure. This is how we see the cosmic web, the glittering filaments and clusters, and this is also how we see the gaps. When scientists began analyzing these immense maps, focusing on our own cosmic neighborhood out to a few billion light-years, they noticed something peculiar. In every direction, the number of galaxies was significantly lower than the cosmic average. It was not a small dip. The density of matter around us was only about half of what standard models predicted. Imagine you're standing in a vast, ancient forest. All the maps and guides tell you this forest is densely packed with trees. But when you look around, you find yourself in a clearing so enormous you cannot see the forest walls, with only a few scattered, lonely trees in sight. You would rightly conclude you are standing in a very special and very empty part of the woods. That clearing is the KBC Void. The galaxy surveys are our map, and the redshift measurements are our ruler, and together they reveal we are not in the thick of the woods at all. We are adrift in its grandest, most silent clearing. This underdensity is not an illusion or a trick of perspective. It is a measured fact of our universe. But this fact immediately leads to a deeper, more unsettling question. If we live in a void, what does that do to our measurements of the entire cosmos? This profound emptiness around us might hold the key to a separate cosmic puzzle, one written in the oldest light in the universe. That light is the cosmic microwave background, a faint afterglow from the Big Bang that fills every corner of space. It is the universe's baby picture, and when we look at this picture, we see a strange, fundamental feature. It is almost perfectly uniform, but not quite. One half of the sky appears very slightly warmer, and the opposite half very slightly cooler. This temperature difference is called the cosmic microwave background dipole. Scientists interpret this pattern as a Doppler shift, meaning our entire local group of galaxies is moving at an incredible speed, over 600 kilometers per second, relative to this primordial background. For decades, the question has been, what are we moving toward or away from? What immense structure could be pulling us with such force? The leading theory points to distant, massive superclusters like the Shapley attractor, a colossal concentration of matter hundreds of millions of light-years away. But there is a problem. The pull from these distant structures, while immense, does not fully account for the staggering speed we observe. Something seems to be missing from the calculation. This is where our location in the KBC Void offers a compelling, elegant solution. Think of gravity not just as a pull, but as a push and pull from all directions. In a universe of average density, the gravitational forces from surrounding matter would roughly balance out. But we are not in an average place. We are in a void, a region of profound underdensity. Picture yourself floating in a swimming pool. If the water is evenly deep all around you, you stay put. But if you are floating above a deep drain, a region where there is suddenly much less water beneath you, the pressure from the deeper water around you will push you toward that drain. In a similar gravitational sense, the KBC Void is our cosmic drain. The lack of mass around us means there is less gravitational pull holding us in place from all sides. Meanwhile, the immense, dense walls of the cosmic web that border our void exert their full, unbalanced pull. We are not just being pulled toward the dense regions, we are also being pushed from the empty ones. This combination could perfectly explain our high-speed motion through the cosmos. Our journey is not just toward something, it is also away from nothing. This theory beautifully ties a local anomaly, our empty neighborhood, to a universal signal, the ancient glow of the Big Bang. It suggests the quiet desert we call home is actively shaping our path through the universe. This central placement within a void forces us to confront one of the most sacred assumptions in all of cosmology. It is called the cosmological principle. In simple terms, this principle states that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the matter in the cosmos is evenly spread out, like raisins in a well-mixed loaf of raisin bread. Isotropic means it looks the same in every direction, with no central point or preferred edge. This idea is not just a philosophical preference, it is the bedrock upon which our entire understanding of the universe's expansion, its age, and its fate is built. Our equations and models all assume that, if you zoom out far enough, every place in the universe is essentially like every other place. There is no special spot. But the KBC Void presents a direct and profound challenge to that assumption. We appear to be sitting in a region of space that is definitively not like other places. It is a bubble of underdensity so vast it constitutes a significant fraction of the observable universe, and we are not just passing through it, we are at its very heart. This arrangement feels unsettlingly special. It raises a provocative and humbling question. Could it be that we, by pure cosmic coincidence, live in an exceptionally unusual and empty part of the cosmos? The scientific and philosophical weight of this question is immense. If the cosmological principle does not hold, if the universe is not smooth on the largest scales we can measure, then many of our fundamental measurements could be systematically wrong. Our calculation for how fast the universe is expanding, a number called the Hubble constant, could be off because we are measuring it from inside a bubble. Our estimates for the amount of dark matter and dark energy could be skewed by our lonely vantage point. It is like trying to determine the global climate by taking temperature readings only from the middle of the Sahara Desert. Your data would be accurate for your location, but it would not represent the whole planet. This is the core dilemma. Either we have been incredibly unlucky in our cosmic address, living in a rare quiet zone that misleads our telescopes, or our foundational principle about the universe's uniformity needs a serious revision. Both possibilities are deeply consequential. One suggests a staggering cosmic coincidence that placed life in a void. The other suggests we must rewrite the textbooks on how the universe is structured. This is not a minor technical debate. It is a fundamental reevaluation of our place in the grand scheme of things. That sacred assumption of a uniform universe is now under direct fire, and the battlefield is the KBC Void itself. Is this billion-light-year emptiness a real feature of the cosmos, or a grand illusion born from our limited perspective? This question has ignited a fierce and fascinating debate at the very frontier of cosmology. On one side are the researchers who map the void, convinced by the sheer scale of the underdensity in the data. On the other side are skeptics who argue the evidence is not yet strong enough to topple the cosmological principle. Their critique centers on two powerful ideas, statistics and bias. First, the statistics. The universe is a wildly lumpy place full of clusters and gaps. Could the KBC Void simply be a natural, albeit very large, fluctuation? Skeptics run sophisticated computer simulations of the cosmos based on our standard models, and yes, sometimes these simulations produce vast, empty regions. The question is one of probability. Is our void so exceptionally large and empty that it should not exist in a statistically uniform universe? Some analyses suggest it might be right on the edge of plausibility, a rare but possible fluke. Others calculate it is an extreme outlier, a one-in-a-million cosmic anomaly. This statistical tug-of-war is far from settled. Then there is the problem of observational bias, the possibility that we are not seeing the full picture. Our most detailed maps of the distant cosmos come from telescopes on Earth and in space that peer out along specific lines of sight. but our own Milky Way galaxy gets in the way. A thick band of gas and dust along the plane of our galaxy obscures our view of the universe beyond, creating a blind spot astronomers call the zone of avoidance. It is as if we are trying to map a forest while standing behind a very wide tree trunk. We cannot see what lies directly behind it. Could it be that hidden behind this galactic curtain are dense clusters of galaxies that, if counted, would fill in our void and make our neighborhood seem average? Proponents of the void counter that their measurements account for this zone, using other wavelengths of light to peer through the dust, and that the underdensity persists in all other directions. But the uncertainty remains a potent argument for skeptics. Furthermore, different teams analyzing the same galaxy survey data sometimes draw different conclusions. Some alternative analyses suggest the underdensity might not be a single, coherent bubble, but rather a looser collection of smaller voids, making it less exceptional. Or perhaps our methods for estimating galactic distances, the very foundation of our three-dimensional map, have subtle systematic errors that amplify the appearance of emptiness. This is not a conflict of personalities, but the rigorous, essential process of science at work. Every claim is met with scrutiny, every data point challenged. The existence of the KBC Void is not yet a settled fact in textbooks. It is a living hypothesis, a thrilling mystery being actively investigated with every new sky survey and telescope. This debate is not a sign of failure, but of a field vibrantly alive, grappling with a discovery that could fundamentally reshape our cosmic self-portrait. To resolve this cosmic debate, scientists turn to the most powerful tools at their disposal, not telescopes but supercomputers. These machines allow us to run the ultimate cosmic experiment, to build a virtual universe from the ground up and see if it looks anything like our own. The most famous of these digital cosmos is the Millennium simulation. Starting with a nearly smooth soup of matter and energy just after the Big Bang, and governed by the laws of physics as we understand them, the simulation lets gravity work its magic over billions of virtual years. The recipe it follows is our current best model of the cosmos, known as lambda CDM, which stands for lambda cold dark matter. This model proposes that the universe's fate is shaped by the interplay between dark energy, represented by lambda, which drives expansion, and cold dark matter, an invisible form of matter that provides the gravitational scaffolding for everything we see. When you press play on this simulation, something beautiful and familiar emerges. From that initial smoothness, gravity begins to pull. Tiny ripples of density grow. Dark matter clumps first, forming an invisible cosmic skeleton. Ordinary matter, the gas that will become stars and galaxies, then flows along this dark framework. Over eons, the structure we observe snaps into sharp, breathtaking focus. A vast, intricate cosmic web materializes with brilliant clusters at the intersections of shimmering filaments, all separated by enormous dark voids. This is a profound validation. Our best models of physics, when run forward in time, naturally create a universe that looks strikingly like the one our telescopes reveal. It means voids are not mistakes or accidents. They are an essential, predicted feature of cosmic architecture. They are the inevitable empty spaces in the grand gravitational tapestry. So the question shifts. The debate is no longer about whether voids can exist, but about the specific size and emptiness of our own KBC void. Does the Millennium simulation, and others like it, routinely produce voids 2 billion light-years across with a galaxy sitting perfectly at its center? Or is our home an extreme statistical outlier? The answer, as you might expect, lies in a gray area. These simulations do produce vast voids, some approaching the scale of the KBC. They show that large underdensities are possible within the standard model. However, a void of this precise scale, with this degree of emptiness and with a central observer, appears to be very rare. Some analyses suggest it sits at the very edge of statistical plausibility. It is like rolling a pair of dice 1,000,000 times. you will eventually get a sequence of 10 consecutive sixes. It is possible, but it is so unlikely that if you saw it happen, you might start to wonder if the dice were weighted. The KBC Void, for some cosmologists, feels like that run of sixes. Its existence does not outright break the lambda-CDM model, but it strains it. It asks a probing question of our virtual universes. Why don't they look more like this? This statistical tension is precisely what keeps the debate alive and urgent. It means that whether the void is real or not, its proposed existence is already doing its job, pushing our models to their limits and forcing us to look deeper into the darkness. Our quiet corner of the cosmos might be distorting one of the most critical numbers in all of science, the Hubble constant. This number represents the rate at which the universe is expanding, a fundamental parameter that tells us the age, size, and ultimate fate of everything. For years, cosmologists have faced a growing and embarrassing problem. We have two primary ways to measure this expansion rate, and they stubbornly refuse to agree. The first method looks back to the universe's infancy, analyzing the subtle patterns in the cosmic microwave background, that ancient afterglow. This gives us a precise measurement of how fast the universe was expanding nearly 14 billion years ago. The second method looks at our local, modern universe. We observe distant supernova, brilliant exploding stars whose known brightness allows us to gauge their distance. By measuring how fast these galaxies are moving away from us, we get a direct read on the expansion rate today. According to our best models of cosmic evolution, these two numbers should line up perfectly. The early universe measurement should flow smoothly into the modern one, but they do not. The local measurements using supernova and other nearby markers consistently give a higher value for the Hubble constant. The universe appears to be expanding faster in our present-day neighborhood than the baby picture of the cosmos predicts it should be. This mismatch is not a small statistical glitch. It is a significant and persistent gap that has withstood over a decade of increasingly precise observations. Cosmologists call this the Hubble tension, and it represents a genuine crisis. It suggests something is fundamentally wrong, either with our measurements, our models, or our understanding of physics itself. This is where our location in the KBC Void offers a tantalizing and elegant solution. Think of the universe's expansion not as a uniform stretch, but as a process influenced by gravity. Dense regions like superclusters have immense gravitational pull. This pull acts as a drag, slowing down the expansion of space within and around them. Conversely, in empty regions like voids, there is very little matter to exert a gravitational brake. In these vast bubbles of nothing, space is freer to expand, and it does so at a slightly faster rate than the cosmic average. Now, remember where we are making our local measurements of the Hubble constant. We are sitting at the center of a billion light-year underdensity. Our telescopes are pointed at supernova and galaxies that are, for the most part, also inside this same cosmic bubble. We are, in effect, measuring the expansion rate of the void, not the expansion rate of the universe as a whole. It is like trying to determine the average speed of cars on a continent by only using a radar gun in the middle of the Autobahn, Germany's famous highway with no speed limit. Your measurement would be accurate for that stretch of road, but it would be much higher than the true continental average, which includes city streets and country lanes. If we are indeed inside a vast void, then our local measurement of the Hubble constant would naturally be inflated. The space in our neighborhood is expanding faster because there is less gravity holding it back. Meanwhile, the measurement from the cosmic microwave background gives us the true global average because it reflects the entire universe at a much earlier time, before such large voids had fully formed. This single idea could resolve the tension. The two methods are not measuring the same thing. One is measuring the universe, the other is measuring our unusually empty part of it. The implications are staggering. It would mean the Hubble tension is not a sign of new, exotic physics or broken models, but a colossal cosmic illusion created by our special address. Our quiet desert home would not just be a curiosity, it would be the reason we have misjudged the pace of the entire cosmos. The void would transform from a strange feature on a map into the key that unlocks cosmology's greatest modern puzzle. But this cosmic illusion leads to a deeper, more personal question. Could our location in this immense void be more than just an accident of statistics? Could it, in fact, be a necessary condition for our very existence? This idea touches on the anthropic principle, a philosophical notion that any observation we make about the universe must be compatible with the fact that we are here to observe it. We do not see the universe from a random point, we see it from a point that allows for observers. And a quiet, empty cosmic neighborhood might be the perfect sanctuary for life to take root and flourish. Consider the alternative. Imagine if our Milky Way resided in the heart of a dense supercluster, a glittering galactic metropolis. The night sky would be ablaze with the light of countless nearby galaxies, a breathtaking but deadly spectacle. In such a crowded environment, the gravitational dance of galaxies is a violent, chaotic affair. Close encounters and direct collisions would be common. Our stable spiral disk, the cradle of our solar system, could be torn apart by a passing galaxy's gravity long before life had a chance to evolve beyond single cells. The sheer density of stars would mean a much higher rate of nearby supernova, catastrophic explosions whose blasts of radiation could sterilize planets and strip away atmospheres. And at the centers of these dense clusters, monstrous black holes often power brilliant, deadly quasars, flooding entire galaxies with lethal X-rays and gamma rays. It is a cosmic environment of constant fireworks and extreme peril. Now contrast that with our reality. We float in the serene emptiness of the KBC Void. Our closest major galactic neighbor, the Andromeda Galaxy, is on a slow-motion collision course, but that impact is billions of years in the future. Catastrophic galactic mergers are rare events in our local group. Devastating supernovae are thankfully distant. The violent cores of active galaxies are far away, their deadly beams pointing elsewhere. For over 4 billion years, Earth has enjoyed a remarkably stable, quiet orbit around a stable star in a stable region of a stable galaxy. This prolonged cosmic peace may not be a coincidence of time and place, but a direct consequence of our address in the grand cosmic web. The void has granted us the ultimate gift, isolation. It has provided the uninterrupted stretches of deep time necessary for the slow, intricate dance of chemistry to become biology, for simple molecules to complexify into conscious beings who can look up and wonder about the emptiness that made them possible. Our existence might be the most compelling evidence that we live in a special, sheltered part of the cosmos, not despite the void, but because of it. Yet even this cosmic desert is not a perfect vacuum. Within the KBC Void, far from the brilliant cities of the cosmic web, a sparse and lonely ecology persists. The most obvious inhabitants are the void galaxies themselves. These are not the grand, majestic spirals like our Milky Way, which thrive in denser neighborhoods rich with gas for new stars. Void galaxies are often small, irregular, and strangely anemic. They are cosmic castaways, isolated islands that formed from the meager scraps of matter within the void, or were gently nudged into the emptiness long ago. Without frequent encounters with other galaxies to stir up their gas and trigger new star formation, many have become quiet, aging places. Their star-making factories have mostly shut down, leaving them with an older, redder population of stars. They are the quiet hermits of the cosmos, glowing faintly in the immense dark. The space between these lonely galaxies is not truly empty either. It is filled with the intergalactic medium, a whisper-thin soup of incredibly hot, ionized gas. This gas is so diffuse that in a volume of space the size of your average living room, you would find only a single atom or two. Yet, spread across billions of light years, it contains a significant portion of the universe's ordinary matter. This gas is not uniform. It traces the ghostly architecture of the void, forming vast, faint clouds and filaments that are nearly impossible to see directly, but whose presence is inferred by how they absorb the light from distant quasars shining through the emptiness. It is the faint, hot breath of the void itself, and then there is the unseen scaffold, dark matter. Even here, in the region of greatest underdensity, the mysterious gravitational glue of the cosmos is present. While dark matter is concentrated in the dense walls and filaments of the cosmic web, it forms a far more tenuous but still present web throughout the void. This subtle dark matter framework is what guided the little ordinary matter there was into forming those isolated void galaxies in the first place. It means the void is not a featureless whole, but a bowl of incredibly subtle gravitational texture, a landscape so faint we can barely perceive it. Finally, consider the true nomads of the void. When galaxies interact or collide, they can fling stars and even entire planets out into intergalactic space at tremendous speeds. These rogue objects are then untethered from any galaxy, doomed to drift forever in the darkness. Within a void, the journey for such a star or planet is profoundly lonely. It would travel for millions, perhaps billions of years, its night sky devoid of any celestial neighbors, illuminated only by the diffuse glow of distant galaxy clusters on the far-off walls of its prison. It is a chilling thought that within this apparent nothingness there may be countless frozen, dark worlds on endless, solitary voyages, so the void is not a sterile place. It is a rich, if desperately sparse, ecosystem with its own unique inhabitants, from aging galactic hermits and hot, thin gas to dark matter ghosts and orphaned worlds. This changes the very meaning of emptiness. This profound isolation we experience today is only a prelude to a future of even deeper solitude. The fate of our cosmic desert, and indeed of all structures in the universe, is being written by a mysterious force, dark energy. While gravity pulls matter together, weaving the cosmic web, dark energy does the opposite. It is a property of empty space itself that causes the expansion of the universe to accelerate. Think of it as a relentless, repulsive pressure embedded in the fabric of reality. Today, its influence is subtle, but over the eons, it will become the dominant architect of the cosmos. In the far, far future, dark energy will not just expand the universe, it will begin to tear the cosmic web apart. The delicate filaments of galaxies, those glittering threads that connect the dense clusters, will be the first to go. As space itself stretches at an ever-increasing rate, the gravitational bonds holding these vast structures together will be overwhelmed. The filaments will stretch, thin out, and eventually snap. The grand, interconnected metropolis of the cosmic web will begin to fracture into disconnected boroughs. Our KBC Void will not remain static in this era. It will actively participate in this cosmic dissolution. As expansion accelerates, the void will likely grow even larger, its borders pushing outward. It will begin to merge with neighboring voids, swallowing the thinning filaments that once separated them. This will create ever greater realms of nothingness, supervoids of unimaginable scale. For the galaxies that currently cling to the fringes of our void, this future is one of exile. As the space between them and the void's center expands faster and faster, their gravitational connection to the rest of the web will be severed. They will be pulled away, their light red shifting into invisibility until they vanish from the view of any future observer within our local group. Our own small cluster of galaxies, the Milky Way, Andromeda, and their satellites will become the ultimate island. Having long since merged into a single, giant elliptical galaxy, this future Milky Way will find itself in a terrifyingly empty cosmos. The walls of the cosmic web, those distant, glowing cities of galaxies, will have receded beyond the cosmological horizon. Their light will no longer be able to reach us as the space between us expands faster than light can travel across it. The night sky for any beings alive in that distant epoch will be almost black. Only the faint, aging stars of their own galaxy will remain visible. The brilliant tapestry of the cosmic web, the evidence of a once-connected universe, will be lost to them forever. They will live in a true island universe, floating in an eternal and growing sea of darkness, with no evidence that other islands ever existed. This is the ultimate destiny dark energy scripts, a cold, quiet dissolution of all structure into isolated specks in an infinite, empty void. To understand the true shape of our cosmic desert, we must learn to see its edges. Astronomers do this by mapping the transition from profound emptiness to the bustling structures beyond. They are searching for the walls of the void, the dense shells of galaxies that mark the boundary between our underdensity and the average universe. This is not a simple search for a line on a map. It is a forensic investigation of gravity's subtle fingerprints on thousands of galaxies. The primary tool for this investigation is a three-dimensional atlas of the cosmos, a pointillist painting made of millions of galactic positions. In these stunning visualizations, our local group is a single, highlighted pixel at the very center of a vast spherical cavity. As you move outward from that central point, the map shows a sparse, lonely sea for hundreds of millions of light years. Then, gradually, the points begin to thicken. The void's shell emerges not as a sharp, solid barrier, but as a statistical increase in density, a gentle brightening in the cosmic fog. This is where the cosmic web begins its intricate weave. To confirm these walls are real and dynamic, scientists look beyond simple positions. They measure something called peculiar velocity. This is a galaxy's own motion through space, separate from the universe's overall expansion. Think of it like this: if the universe's expansion is a steadily flowing river carrying all galaxies along, a peculiar velocity is a fish swimming against or with that current. By carefully measuring the redshifts and distances of galaxies on the suspected edge of the void, astronomers can calculate these peculiar motions. What they hope to find is a pattern, a gravitational signature. If the KBC Void is a real underdensity, then the galaxies on its inner edge should be experiencing a peculiar pull. The immense mass of the dense walls surrounding the void should be gravitationally tugging on them, drawing them outward, away from the empty center. It would be like water slowly draining from a basin, with galaxies on the sloping sides feeling a gentle pull toward the brim. Observing this outward flow would be powerful, direct evidence that the void is not just a coincidence in a map, but a coherent structure with measurable gravitational effects. Conversely, if no such pattern exists, if the motions are random, it would suggest our perceived emptiness might be a looser collection of smaller gaps without a unified identity. This painstaking work of mapping shells and measuring subtle flows is how we move from seeing a strange pattern in the data to confirming the architecture of our cosmic home. It transforms the void from a statistical curiosity into a physical place with borders we can, in theory, one day point to and say, there, that is the edge of our solitude. The search for the void's walls forces us to confront a more radical possibility. What if the strange motions we see are not caused by a giant hole in space, but by a fundamental flaw in our understanding of gravity itself? For centuries, we have relied on Isaac Newton's and later Albert Einstein's laws of gravity to explain everything from falling apples to orbiting planets. These laws work spectacularly well in our solar system and within galaxies, but on the vast scales of the cosmic web, some scientists wonder if gravity might behave differently. This is not a mainstream view, but a fringe idea that challenges the very bedrock of physics. It suggests we may not need dark matter or a colossal void to explain the strange pulls and pushes we observe. Instead, our equations for gravity might simply be incomplete. One of the most discussed alternatives is called modified Newtonian dynamics, or MN. This theory proposes that gravity does not fade as quickly with distance as Newton's law predicts. In regions of extremely weak gravity, like the outer fringes of galaxies or the deep emptiness between them, a subtle extra kick of gravitational force emerges. The implications are profound. If Mund is correct, many of the phenomena we attribute to the gravitational pull of invisible dark matter could instead be explained by this modified law. Galaxies would hold together at their edges not because of unseen halos of dark matter, but because gravity itself is stronger there than our textbooks say. So how does this connect to our cosmic void? If gravity behaves differently on large, empty scales, it could completely alter our interpretation of the evidence. That high-speed motion we measure, the cosmic microwave background dipole that suggests we are flying through space, might not be caused by the gravitational push of a void's emptiness. It could be a signature of this modified gravity at work, a subtle warping of spacetime's rules that makes it merely appear as if we are in an underdense region. Similarly, the apparent faster expansion rate we measure locally, the Hubble tension, might not require us to live in a special bubble. It could be a natural consequence of gravity's altered behavior over cosmic distances, making empty space expand in a way our standard models do not predict. This idea turns the problem inside out. Instead of asking, how does a giant void distort our measurements, we ask, what if our measurements are correct and our laws of physics are wrong? The void, in this view, might not be a physical structure at all, but a kind of mirage created by our misunderstanding of the universe's most fundamental force. It is a breathtakingly elegant, if controversial, solution. It seeks to erase two great cosmic mysteries, dark matter and the anomalous void, with a single stroke by rewriting the rules of gravity. Yet for all its elegance, the modified gravity hypothesis faces immense hurdles. It struggles to explain all the evidence that supports the standard model, particularly the detailed patterns seen in the cosmic microwave background and the behavior of colliding galaxy clusters. Most cosmologists still see dark matter and dark energy as the more complete, though puzzling, framework. But the very existence of this radical alternative is a testament to how deeply the KBC Void mystery cuts. It shows that when faced with data that strains our models to the breaking point, scientists are willing to question even their most cherished assumptions. Whether the void is a real place or a gravitational illusion, its shadow is forcing us to look at the cosmos in entirely new ways. Our cosmic desert is not the only one of its kind. The universe is pockmarked with voids, great bubbles of nothingness that punctuate the cosmic web. Perhaps the most famous is the Boötes Void, discovered in the 1980s. For a time, it was nicknamed the Great Nothing. This void is roughly 330 million light-years across, a staggering emptiness where astronomers expected to find thousands of galaxies but found only a few dozen. Yet compared to our proposed home, the Boötes Void is a relative puddle. The KBC Void, if confirmed, is nearly 7 times wider. Another notable structure is the southern local supervoid, an underdense region in the constellation Eridanus that aligns with a mysterious cold spot in the cosmic microwave background. These are not anomalies, they are features. Voids come in a range of sizes, from a few tens of millions to over 1 billion light-years across. They are the empty chambers in the universe's vast, glittering honeycomb. So what makes the KBC Void special, if anything? Its primary claim to uniqueness is its scale combined with our central position within it. A void 2 billion light-years wide is at the extreme upper limit of what our standard models of cosmology predict should exist. Finding one is rare. Finding yourself at the dead center of one is statistically, almost absurdly unlikely. This is the core of the controversy. It feels too special to be true. But there is another, more intriguing possibility. Perhaps the KBC Void is not a freakish outlier, but a signpost. Maybe we are only now developing the tools and maps to see that the universe is far more frothy and bubbly than we ever imagined, with giant voids being more common than our current surveys suggest. Our view of the cosmos has always been limited by the reach and sensitivity of our telescopes. For decades, our three-dimensional maps were like early navigational charts, showing coastlines but missing entire continents. The Boötes Void was a shocking discovery because it was so large and so empty, visible even in the relatively shallow surveys of the time. The KBC Void is a subtler, more extended structure, its full dimensions only coming into focus with deeper, more comprehensive galaxy censuses. This leads to a profound question: are we finally seeing the true architecture of the cosmos, or is our own void still an exception that breaks the rules? The answer is coming, and it will be delivered by a new generation of cosmic cartographers. The Vera C. Rubin Observatory, currently under construction in Chile, will soon begin the legacy survey of space and time. This project will be a revolution in scale. Over 10 years, its enormous mirror and giant camera will scan the entire southern sky every few nights, not once but over and over. It will not just take pictures, it will create a dynamic, living movie of the cosmos. The survey is expected to detect and measure the distances to billions of galaxies, pushing our detailed maps of the cosmic web out to unprecedented depths. It will peer into the zone of avoidance, using infrared eyes to see through the dust of our own galaxy. When this flood of data arrives, we will have our most definitive census yet of the large-scale structure of the universe. The legacy survey of space and time will almost certainly find more giant voids. It will measure their shapes, their distributions, and their precise emptiness. We will learn if the KBC is truly a lonely giant, or if it is merely the first of many such colossal bubbles we have stumbled upon. This survey will either solidify the challenge to the cosmological principle or finally reveal our place as a rare, but not impossible, statistical fluke in a universe that is, on the largest scales, uniform after all. The darkness we perceive may soon be filled with the light of billions of new data points, revealing whether our solitude is a local condition or a fundamental feature of the cosmos. The origin of our cosmic desert is written in the first trillionth of a second after the Big Bang. To understand the void, we must become cosmic archaeologists, tracing its lineage back to the most microscopic seeds of reality. The story begins not with a bang, but with a quantum whisper. In the searing, dense furnace of the newborn universe, space itself was a turbulent sea of energy. According to our best theories, the cosmos underwent a period of unimaginably rapid expansion called inflation, stretching a subatomic speck of space to a size larger than our observable universe in a fleeting instant. During this violent stretching, quantum fluctuations, tiny random variations in energy that flicker in and out of existence at the smallest scales, were not smoothed away. Instead, inflation magnified them, stamping these microscopic ripples onto the fabric of the cosmos. These ripples became the blueprint for everything, the ultimate cosmic fingerprint. Where the ripple was a slight peak, a region of marginally higher density, gravity would later find a foothold. Where it was a trough, a region of slightly lower density, a different fate awaited. This is the profound and beautiful idea. The glittering cities of the cosmic web and the desolate voids between them all grew from the same set of random, microscopic seeds. After inflation ended, the universe was a nearly smooth, hot plasma, but imprinted with these faint density patterns. For hundreds of thousands of years, it was too hot for atoms to form, and light was trapped, bouncing endlessly between particles. Then, in an event called recombination, the universe cooled enough for atoms to coalesce, allowing light to travel freely. That released light is the cosmic microwave background we see today, and its subtle temperature variations are a direct snapshot of those primordial density ripples. The slightly cooler spots in this ancient glow correspond to regions of slightly lower density, the future homes of voids. The slightly warmer spots are the future homes of galaxy clusters. The die was cast. Gravity is the sculptor that then spent billions of years carving this raw material. In the overdense regions, gravity pulled matter together, building the dense knots and filaments of the cosmic web. But in the underdense regions, something equally important was happening: expansion. A region with a little less matter feels a little less gravitational pull from within itself. This allowed space inside that region to expand a bit faster than the cosmic average. Think of the universe as a rising loaf of raisin bread. Most raisins are clustered, but a few are isolated. As the dough rises, the empty spaces around those isolated raisins expand more quickly because there's less dough holding them back. Over cosmic eons, this difference compounds dramatically. The underdense region expands faster, becoming ever more empty relative to its surroundings, while gravity relentlessly drains any remaining matter out of it and into the growing filaments around its edges. What began as a faint, cooler patch in the afterglow of creation slowly grew into a vast, emptying bubble, a void in the making. Supercomputer simulations let us watch this epic transformation in fast forward. We start the simulation with the smooth, rippled plasma of the early universe, governed by the laws of physics. Press play, and gravity begins its slow, relentless work. First, the dark matter, which feels gravity but not light, begins to clump into an invisible skeleton. Ordinary matter, the gas that will become stars, then flows along this dark framework. You can see the overdense regions brighten into glowing knots connected by shimmering threads, and between them, the underdense regions darken and stretch. They do not just sit there, they actively evolve. As the filaments grow thicker and more defined, they act like cosmic drains, pulling matter from the void interiors. The void expands, its boundaries sharpening. Over billions of simulated years, a clear cosmic web emerges, with voids as its dominant feature. Our local underdensity, the KBC Void, would have followed this exact script. That faint quantum trough in our neighborhood was destined over 13.8 billion years to become the billion light-year emptiness we potentially inhabit today. We are not living in a random hole punched in the cosmos. We are living inside a natural, predicted feature that grew according to the universe's own rules from its first fleeting moments. Our solitude has a pedigree stretching back to the beginning of time. This profound emptiness makes voids the ultimate laboratories for dark energy. While gravity sculpts the dense knots and filaments of the cosmic web, dark energy dominates the vast, empty spaces in between. Within a void, there is very little matter to exert a gravitational pull, so the repulsive push of dark energy operates almost unchallenged. It is here, in these bubbles of near-nothingness, that we can witness the purest signature of the force that will decide the fate of everything. To understand why, think of a void not as a static hole, but as a living, evolving structure. Over billions of years, gravity tries to pull matter into the void from its denser edges, slowly filling it in. Dark energy does the opposite, accelerating the expansion of space itself, which stretches the void larger and makes it even emptier. The history of the cosmos is a tug of war between these two titanic forces, gravity versus dark energy, and the shape and growth rate of a void records the outcome of that struggle. By measuring how voids have changed over cosmic time, we can take the universe's vital signs. For instance, if dark energy is constant and unchanging, as our simplest models assume, voids will expand in a predictable, smooth way. But if dark energy's strength has varied over the eons, becoming stronger or weaker, that history would be imprinted in the void's architecture. A void that grew more rapidly in the past than it does today would tell a different story than one that is now accelerating its own expansion. The KBC Void, as a nearby giant, offers us a front-row seat to this cosmic contest. Because it is relatively close, we can map its structure and the motions of the few galaxies within it with exceptional detail. We can measure whether its boundaries are sharp or fuzzy, whether galaxies on its edges are flowing outward in a steady drain, or if that flow is accelerating. Each of these details is a data point about the strength of dark energy in our local universe. This turns our cosmic desert from a curiosity into a crucial instrument. It is a natural telescope focused not on distant stars, but on the fundamental properties of space itself. By decoding the growth record of the KBC Void and others like it, we are not just studying emptiness, we are reading the autobiography of dark energy, written in the expanding silence between the galaxies. Crossing this billion light-year emptiness would be the ultimate test of any future civilization. To reach the nearest vibrant filament of the cosmic web, the bustling galactic highway beyond our desert, you would face a journey of incomprehensible scale. Even traveling at 99.99% the speed of light, a feat far beyond any technology we can conceive, the trip would swallow millions of years from the perspective of the universe outside. For the travelers themselves, thanks to the strange time dilation of relativity, the subjective journey might only be a few centuries, but that is where the practical nightmare begins. A voyage through a supercluster is like sailing a well-provisioned ship across a teeming ocean. You pass by countless stars, each a potential port for refueling, for harvesting raw materials, or simply for a change of scenery. Nebulae offer clouds of gas to collect. Planetary systems might provide fresh water and minerals. The journey, while long, is filled with waypoints and resources. The void offers none of that. It is the cosmic equivalent of attempting to row a lifeboat across the Pacific Ocean, but a Pacific that has been drained of all water, all fish, all islands. For millions of light years in every direction, there is almost nothing to use. No nebulae to scoop for hydrogen fuel, no asteroid belts to mine for ship repairs. No stray comets or rogue planets to offer a scrap of raw material. Your vessel would need to carry every single atom of fuel and every spare part for the entire voyage at the outset, a logistical impossibility for any journey of such staggering length. The isolation would be absolute. For centuries of ship time, the view from the observation deck would be a profound and unchanging darkness. The Milky Way, and eventually all the galaxies of the local group, would shrink to a faint, receding smudge of light astern. Ahead, the destination filament would not appear to grow closer for generations. It would hang in the void, a distant, teasing mirage of civilization. The psychological toll of this would be unimaginable. You are not just leaving home, you are watching home vanish from the universe, committing to a path where for thousands of generations of those you left behind, you are simply gone. The silence outside would be matched by a crushing silence within, broken only by the hum of the ship's systems and the knowledge that should anything fail, there is no hope of rescue, no possibility of sending a distress signal that would reach anyone in time. This is the true meaning of living in a void. It is not just a location on a map, but a condition of profound and inescapable separation, a barrier woven from emptiness itself that defines the possible horizons of any society born within its bounds. This profound isolation rewrites the very logic of the search for other minds in the cosmos. Our unique address in the KBC Void forces us to reconsider the search for extraterrestrial intelligence, or SETI, from a startling new perspective. If our reasoning holds that stable, quiet galactic neighborhoods are essential cradles for complex life, then voids might not be deserts at all, but sanctuaries. They could be the cosmic equivalents of remote mountain valleys, peaceful places where civilizations can evolve over eons without constant cosmic disruption. In this view, the vast bubbles of emptiness we see might be the most likely homes for intelligence, not the least. The brilliant, crowded superclusters could be beautiful but barren, their frequent cataclysms resetting the evolutionary clock too often for technological species to ever emerge. This flips the traditional SETI assumption on its head. For decades, we have pointed our radio telescopes toward dense star fields and nearby galaxies, thinking more stars meant more chances for life. But if the void hypothesis for life is correct, we have been listening to the cosmic cities while the hermits in the desert remain silent. Our entire search strategy may be biased, aimed at the flashy but lifeless metropolises while missing the subtle signals from the quiet towns. Yet this sanctuary idea has a dark mirror image. Consider our own efforts to be heard. For over a century, our television and radio broadcasts have been leaking into space, forming an expanding bubble of human noise now over 200 light-years across. In a typical region of the universe, that bubble would have already washed over thousands of galaxies. But we are not in a typical region. Our bubble is expanding primarily into the KBC Void. Imagine that bubble as a ripple on a pond. In a normal pond, the ripple would quickly reach many distant shores, but our pond has a vast, empty center. Our ripple races outward, encountering nothing but more empty water for distances so vast it numbs the mind. By the time our first television signals reach the dense walls of the cosmic web, where galaxies are plentiful, they will be so faint and diluted as to be indistinguishable from the background crackle of the universe. Our most powerful intentional messages, like the Arecibo transmission, face the same fate. They are like messages in a bottle, cast into an ocean that is almost entirely shoreless. This leads to a chilling and elegant resolution to the famous Fermi paradox, the question of why, if the universe is so vast and old, we see no evidence of other civilizations. Enrico Fermi famously asked, "Where is everybody?" The void offers a simple, spatial answer. Perhaps we are alone, not in the universe, but in our void. Advanced civilizations may indeed be common in the universe, but they are clustered in the dense filaments and superclusters, those glittering galactic highways where communication and travel between stars might be feasible. We, however, evolved in a desert so wide that the nearest oasis of advanced life could be hundreds of millions of light-years away, far beyond any plausible detection or contact. The silence we hear is not a universal silence, it is a local one. We are the isolated village on a remote island, unaware that over the horizon, across an uncrossable sea, entire continents of civilization thrive. Our cosmic desert has protected us, but it has also imprisoned us in a solitude of our own making, or rather, of gravity's making. The void does not just hide others from us, it hides us from everyone else. The profound silence of our cosmic desert is not just a scientific fact, but a sensory experience. To truly feel its scale, we must move beyond charts and numbers and find new ways to perceive the emptiness. One of the most haunting methods is data sonification, the art of turning scientific information into sound. Astronomers have taken the three-dimensional maps of galaxy surveys, the very data that revealed the KBC Void, and translated them into music. Imagine each galaxy as a single, clear note. In a dense supercluster, the sound would be a roaring, chaotic symphony, a cacophony of countless notes overlapping in a brilliant, overwhelming chord. But when the sonification scans across our local region of space, something extraordinary happens. The music falls into a deep, whispering hush. Notes become rare, isolated events. A single tone might ring out, followed by vast stretches of near silence, punctuated only by the faint, lonely ping of another distant galaxy. The empty space between them is rendered as a low, droning background hum, the sonic signature of the void itself. Listening to it, you do not just understand the underdensity, you feel it in your bones. It is the sound of profound isolation, a musical representation of our place in the cosmos that is both beautiful and deeply unsettling. This auditory map makes the abstract data viscerally real, allowing us to hear the nothingness that surrounds us. Artists and visualizers collaborate with scientists to build bridges between raw data and human understanding. They take those same galactic coordinates and construct immersive, three-dimensional models you can fly through. On a screen, you start at a point representing Earth. With a keystroke, you begin to move outward at an impossible speed. For a long, simulated time, you travel through a sea of utter black, your path illuminated only by the rare, faint glow of a passing void galaxy. Minutes might pass in this simulation before you finally begin to see a faint, glowing latticework in the distance, the walls of the cosmic web. The sheer duration of that empty journey, even in a sped-up simulation, delivers an emotional impact no graph ever could. It makes you wait in the darkness. Other artists create stunning still renderings depicting our local group of galaxies as a tiny, fragile raft of light, adrift in a spherical chamber of black so vast its curved walls are only suggested by the faintest gradient. These works are not mere illustrations, they are philosophical instruments. They force us to confront the emotional and existential weight of our cosmic address, translating petabytes of survey data into a single, gut-punching image of our solitude. This collaboration between art and science is essential. The scales involved, billions of light years, trillions of stars, are simply too large for our everyday intuition to grasp. Our brains evolved to navigate forests and savannas, not cosmic voids. Science gives us the facts, the precise measurements of density and distance, but art gives those facts a form we can feel. It provides the metaphor, the emotional resonance that allows knowledge to become meaning. When you hear the sonification's eerie quiet or lose yourself in a 3D visualization of the endless dark, you are not just learning about the KBC Void, you are experiencing a version of it. These creative tools democratize cosmic wonder, making the frontiers of cosmology accessible to anyone willing to look or listen. They remind us that understanding the universe is not solely an analytical act, but a deeply human one, requiring both the rigor of the telescope and the vision of the artist to make the incomprehensible tangible. The sound of that sonified void, that deep and whispering hush, settles into something more than data. It becomes a feeling. This knowledge of our cosmic geography does not simply exist in textbooks. It seeps into our psyche, reshaping our sense of place in a universe that grows stranger with every discovery. For centuries, we have grappled with revolutions that displaced us from the center of everything. The Copernican revolution taught us Earth is not the center of the solar system. Later, we learned the Sun is a mundane star in a mundane galaxy, lost in a sea of billions. Each step removed a layer of cosmic privilege, pushing us further into the anonymous suburbs. Yet the KBC Void presents a different kind of displacement, a paradox. We are not at the center of the universe, but we might very well be at the center of a giant, billion-light-year sphere of nothing. This is not a demotion to mediocrity, it is an assignment to profound and eerie uniqueness. How are we to process that? The emotional response splits into two powerful currents, isolation and wonder, often flowing together. There is an undeniable chill in realizing that our entire history, every triumph and tragedy, every work of art and act of love, has unfolded in what amounts to a cosmic backwater, a silence so vast it defies metaphor. The philosopher Blaise Pascal, centuries before we knew of galaxies, captured this vertigo when he wrote of the eternal silence of these infinite spaces filling him with dread. That dread is the shadow side of the void, the fear that in such emptiness nothing we do could possibly matter, but another, brighter current runs counter to it. This same emptiness can be seen as the ultimate sanctuary, the quiet room in a chaotic universe where life was given the peace to think. Astronomer and author Carl Sagan often spoke of the pale blue dot, our world as a mote of dust suspended in a sunbeam. The void magnifies that perspective a billionfold. We are not just a pale blue dot, we are a pale blue dot in the grandest cathedral of nothing ever observed. This knowledge injects a fierce, precious value into our existence. If we are alone in this desert, then every thought, every connection, every act of curiosity becomes a brilliant spark against an infinite dark, meaningful precisely because the darkness is so complete. It fosters a radical humility, yes, but also a radical responsibility. We are the universe becomes self-aware in one of its quietest corners. What we choose to do with that awareness, how we care for our fragile dot and the minds upon it, might be the only light for uncountable light years. This is the psychological gift and burden of the void. It strips away any lingering fantasy of cosmic centrality, not to make us feel small, but to make our consciousness feel singular and essential. We are not the kings of creation, we are its most attentive listeners, sitting in the quietest place, hearing the deepest echoes of the Big Bang and daring to ask what they mean. The quiet we hear in the void is a product of immense noise, the digital noise of data. Every three-dimensional map of the cosmos, every subtle detection of an underdensity, is a triumph of data processing on a staggering scale. The same algorithms that sift through the light of millions of galaxies to reveal the cosmic web are not confined to astronomy. They are now finding life-saving applications here on Earth in the human body. The challenge of mapping the universe's large-scale structure is remarkably similar to mapping the intricate wiring of the human brain. In both cases, you have a vast three-dimensional field of points, neurons instead of galaxies, and you need to identify clusters, filaments, and voids in the connections. The sophisticated pattern recognition software developed by cosmologists to trace faint filaments of dark matter is now being adapted by neuroscientists to map the brain's connectome, the complete network of neural pathways. This allows researchers to see how different regions communicate and to identify abnormal patterns that may signal diseases like Alzheimer's or schizophrenia at their earliest, most treatable stages. Similarly, the statistical techniques used to distinguish a true cosmic void from a random fluctuation in galaxy counts are directly applicable to medical imaging. When a radiologist looks at an MRI or a CT scan, they are searching for subtle anomalies in a sea of data, a tumor or a lesion that represents an underdensity or overdensity in healthy tissue. Cosmology's tools for analyzing noisy, large-scale datasets help improve the software that highlights these anomalies with greater speed and accuracy, leading to earlier diagnoses. This is the hidden, practical heartbeat of fundamental research. The drive to understand our place in a void quietly fuels advances that place a stethoscope on a human heart. Beyond medicine, the data science of the cosmos is reshaping how we understand our own world. The algorithms that model the gravitational pull between galaxies to simulate the cosmic web are cousins to those that model the flow of information, money, or even disease through human social networks. Analyzing the structure of the internet, predicting traffic patterns in a megacity, or modeling the spread of a virus all require identifying hubs, clusters, and pathways in immense interconnected systems. Cosmologists, experts in the original big data problem, have spent decades developing methods to handle these complexities. Their work on statistical inference and network theory, born from studying the universe's largest possible network, now provides blueprints for making our man-made networks more efficient, resilient, and understandable. This cross-pollination is a testament to a fundamental truth. Understanding the architecture of the cosmos often teaches us about the architecture of complexity itself, whether it's made of dark matter or human decisions. The hardware of discovery tells a parallel story. The quest to see fainter, farther, and with more precision drives technological innovation at the very edge of the possible. The ultra-sensitive charge-coupled devices, or CCDs, in modern telescopes, designed to capture the faintest photons from the edge of the observable universe, share a direct lineage with the sensors in your smartphone camera. The need to process the torrent of data from sky surveys pushed the development of advanced computing and data storage solutions that later became foundational for cloud computing and large-scale commercial analytics. Even the exotic materials and cryogenic cooling systems developed to keep space telescope mirrors and detectors at near absolute zero have found uses in improving the resolution of medical MRI machines and in the development of quantum computers. Every time an astronomer points a new instrument at the sky to probe the depths of a void, they are not just looking out, they are building tools that eventually look inward into our bodies, our societies, and our technologies. The billion light-year emptiness is not just a subject of study, it is a silent partner in innovation, a cosmic challenge that compels us to build better eyes, better brains, and better tools for all of science. This cosmic desert might sound like a terrifying place, a gaping hole in reality. After all, our stories are filled with monsters from the void, and the word itself conjures images of a hungry vacuum waiting to swallow everything. But we must separate science fiction from cosmic fact. The KBC Void is not a cosmic drain, and it absolutely will not suck us in. The physics here is crucial and surprisingly straightforward. Gravity works exactly the same inside the void as it does everywhere else in the universe. The difference is not in the rules, but in the players. There are simply far fewer sources of gravity within that billion light-year sphere. Think of it like being in a vast, nearly empty field instead of a crowded city square. In the city, you feel the press of the crowd, the bumps and pulls from all directions. In the field, you are simply alone. The emptiness does not pull you. The absence of pull is what defines it. We are not being dragged into the center of the void. We are floating in its quiet center because gravitationally, it is a very balanced, very uneventful place. The immense structures on the void's distant walls exert a gentle pull which contributes to our motion through space, but they are much too far away to ever reel us in. We are not stuck in a whirlpool, we are adrift on a still, dark lake. This leads to another vital clarification. The void is not a dangerous anomaly or a flaw in the cosmos. It is a fundamental, predicted feature of the cosmic web. As natural and inevitable as a valley between mountain ranges, the universe builds these vast, empty chambers as it constructs the glittering walls of galaxies. One cannot exist without the other. Calling the void an anomaly is like calling a desert on Earth a mistake. It is simply one type of landscape in a diverse cosmos. Our position within it does not mean we are doomed or marooned. In fact, as we have explored, this quiet neighborhood may have been our greatest cosmic advantage. It provided the stability and isolation necessary for our solar system to form and for life to evolve over billions of uninterrupted years. The void was not a prison, it was a cradle. The real danger for complex life likely lies in the opposite environment. The brilliant, violent metropolises of galactic superclusters where collisions and radiation are frequent. Our address in the quiet suburbs, far from the gravitational chaos of dense urban centers, might be the very reason we are here to ponder it. So, the next time you hear the word void, replace that sci-fi fear with a sense of awe for a natural, protective, and profoundly spacious part of our home universe. The final proof of our cosmic solitude will not come from theory, but from a new generation of eyes now turning toward the sky. A fleet of revolutionary telescopes, both in space and on remote mountaintops, is poised to deliver the most detailed map of the universe ever created. Their mission is to measure the darkness with unprecedented precision, to trace the void's ghostly borders, and to settle the debate once and for all. Leading this charge is the European Space Agency's Euclid spacecraft. Launched in 2023, Euclid is not just another telescope, it is a dedicated cosmic cartographer. Its 6-year survey will observe billions of galaxies across more than a third of the sky, measuring their shapes and distances with exquisite accuracy. But Euclid's true power lies in a subtle effect called weak gravitational lensing. As light from distant galaxies travels toward us, it is gently bent by the gravitational pull of all the matter, both seen and unseen, in its path. This includes the dark matter that outlines the cosmic web. By meticulously measuring the tiny, distorted shapes of billions of galaxies, Euclid can essentially take an X-ray of the universe's large-scale structure. It will see not just the galaxies, but the invisible gravitational skeleton they cling to. For the KBC Void, this is the ultimate test. Euclid's map will reveal the true density, or lack thereof, of dark matter in our neighborhood. It will show whether the underdensity is a coherent spherical bubble in the dark matter web or a more scattered and less dramatic feature. This data will either solidify the void's reality or dissolve it into statistical noise. Joining Euclid in the mid-2020s will be NASA's and Nancy Grace Roman Space Telescope. Often called Hubble's wide-eyed cousin, Roman will combine Hubble's sharp vision with a field of view 100 times larger. Its primary cosmology survey will peer back over 10 billion years, capturing the light of an estimated 2 billion galaxies. This immense, deep survey will allow scientists to create a three-dimensional movie of cosmic structure formation. We will see how voids like the KBC have grown and evolved over cosmic time. By comparing the size and emptiness of ancient voids to modern ones, astronomers can directly measure the influence of dark energy, testing whether it has remained constant or changed in strength. Roman's data will be particularly powerful for resolving the Hubble tension. By measuring the expansion rate using different cosmic mileposts at various distances, both inside and potentially outside our local underdensity, it will clarify if our faster local measurement is a void-induced illusion or a genuine cosmic mystery. On Earth, the next leap in clarity will come from the Extremely Large Telescope, or ELT, now under construction in Chile's Atacama Desert. With a primary mirror nearly 40 meters across, this ground-based behemoth will collect more light than all of today's large optical telescopes combined. While it cannot survey the whole sky like Euclid or Roman, its unparalleled resolution will act as a cosmic microscope. It will study individual stars within galaxies on the very edge of the suspected void, obtaining pin-sharp measurements of their distances and motions. This will allow scientists to map the void's proposed walls with centimeter-level precision on a continental scale, confirming whether galaxies there are truly flowing outward, pulled by the gravity of the denser regions beyond. The ELT will turn the subtle statistical hints of a void into hard kinematic evidence. Together, this armada of instruments represents a paradigm shift in cosmology. We are moving from sketching the cosmos with a pencil to rendering it in high-definition 3 dimensions. Within a decade, the question of the KBC Void will be answered. We will know its exact dimensions, the sharpness of its edges, and its true gravitational influence on our motion. But perhaps the most thrilling possibility is that these telescopes will not just map our void, they will discover something even more profound. As our maps plunge deeper and see fainter, we might find that the KBC Void is not unique, but merely the first of many such colossal bubbles we have stumbled upon. Or they could reveal structures so vast they make our current cosmic web look like a small-scale pattern, hinting at an architecture of the universe we have not yet dared to imagine. These missions are not just looking for answers, they are opening the door to questions we do not yet know how to ask, redrawing the map of reality from the quiet center of our possible desert. Our journey through the KBC Void has taken us from a startling map of emptiness to the deepest questions of existence. We began by discovering our galaxy's true address, not in a glittering supercluster, but at the heart of a billion light-year bubble of near-nothingness. We saw how this cosmic desert might resolve great puzzles, from our high-speed motion through space to the troubling mismatch in the universe's expansion rate. We pondered whether this profound isolation was not a prison, but a protective cradle, granting life the quiet eons needed to emerge. And we looked to a future where new telescopes will finally measure the void's true shape, settling a debate that challenges our most sacred assumptions about the cosmos. The overarching lesson is both humbling and beautiful. The universe is not a bland, uniform soup. It is a dynamic, structured tapestry, a cosmic web of brilliant filaments and immense dark voids. We do not live in an average place. Our Milky Way, for all its ordinary spiral majesty, resides in an extraordinary pocket of that web. This realization reframes our entire story. We are not lost in a random suburb. We are the attentive inhabitants of a rare and silent sanctuary. So the next time you step outside and look up at the night sky, let your perspective shift. Those points of light are not just stars, they are the nearest neighbors in our local void, glowing across a gulf of darkness that stretches for hundreds of millions of light years. Beyond them lies a structured grandeur we are only beginning to map, a universe of vast emptiness and dazzling light, woven together in a single, breathtaking design. Carry that sense of wonder with you. If you enjoyed this deep dive into the architecture of reality, consider subscribing. We have only begun to explore the cosmos together.